For 70 years now, Jupiter has been sending strange signals, short, rhythmic, similar to Morse code, and in 7 decades scientists have not been able to decipher them. They have not been able to understand what they are. If you translate these signals into sound, you will hear something between the crackling of popcorn in a hot pan and the clattering of stones on a tin roof. Sometimes, the distant sound of the surf, sometimes rhythmic clicks, as if someone were tapping out a code from the depths of space. This is not science fiction. It is reality which we observe every day. A planet the size of 300 Earths continuously transmits something into the void, and we listen, and we do not understand a word. The year is 1955. It is a cold winter in Maryland, 20 miles northwest of Washington. In the middle of farmland lies a strange object, 96 acres of land entangled with wires, 66 dipole antennas connected by 5 miles of cable. The structure resembled a giant cross sprawled across the frozen grass. This is Mills Cross, the Carnegie Institute's radio telescope. Every night, 2 young scientists work here, Bernard Burke and Kenneth Franklin. Their task is simple and routine: to map the radio emissions of the Crab Nebula, the remnant of a supernova that exploded nearly 1,000 years ago. The work requires patience. Night after night, they record data, calibrate equipment, and battle interference. And this is where the strangeness begins. Noise regularly appears on their recordings, sharp bursts similar to terrestrial interference, as if a faulty electric motor is turning on somewhere nearby, or a car with a faulty ignition is passing by. Burke and Franklin note these artifacts time and time again and continue their work. But the interference does not disappear, it returns, and something about it is not right. Earth disturbances are tied to Earth time. They occur when people wake up, go to work, and turn on appliances, but this noise followed a different schedule. Every night it shifted 4 minutes earlier, exactly by the amount that sidereal time differs from solar time. It wasn't an earthly signal, it was something from there. Burke and Franklin began tracking the source. The coordinates pointed to a point that was slowly moving across the sky. They plotted the trajectory on a map of the solar system, and froze. The source was Jupiter. On the 6th of April, 1955, at a meeting of the American Astronomical Society in Princeton, 2 young radio astronomers announced that the planet Jupiter was a powerful source of radio waves. It was the first time in history that humanity had heard the radio voice of another planet. The scientific world was shocked. Radio emissions were known to come from the Sun, distant galaxies, and supernova remnants. But a planet? A cold gas giant 800 million kilometers away from us? Where did it get the energy to shout across the entire solar system? There was no response, but the signals kept coming. Years passed, then decades. Scientists around the world pointed their antennas at Jupiter, recorded thousands of hours of its voice, and gradually began to discern patterns in this chaos. The signals turned out to be non-uniform noise. They were divided into 2 types, each with its own characteristics. The first type is called L bursts, from the word long. They last from a few tenths of a second to several seconds, and if you translate them into sound, you will hear something similar to the sound of ocean waves rolling onto a distant shore. It is a rhythmic, almost soothing sound, but the second type is a completely different matter. S bursts. Short. Each lasts only a few milliseconds, thousandths of a second. They come in series, dozens of pulses per second, and sound like crackling, clicking, or stones hitting metal, or like popcorn popping in a hot pan. It was the S-burst that became the main mystery. On spectrograms, graphs with time on one axis and frequency on the other, they look like slanted lines. Each line starts at a high frequency and rapidly slides downwards. The speed of this drift is monstrous, from -10 to -30 MHz per second. In a fraction of a second, the signal plummets through the entire range, as if something were falling into an abyss. What could have created such a pattern? By the 1960s, scientists had put forward a hypothesis. The source of the signal was not the planet itself. The source was its satellite, a small moon named Io. Io is hell turned inside out. It is the most volcanically active body in the solar system. Hundreds of volcanoes continuously spew sulfur and silicate lava hundreds of kilometers into the air. Jupiter's tidal forces literally crumple this moon, heating its interior to a molten state. But that's not the main thing. The main thing is what's happening between Io and Jupiter. Imagine an invisible tube connecting the Moon to the planet. A tube made of magnetic lines of force, the so-called eomagnetic tube. Electric current flows through this tube, 5 million amps. Power, about 2 trillion watts. It is the largest direct current electrical circuit in the solar system. It surpasses anything ever built by humankind, and it has been operating continuously for billions of years. Io's volcanoes eject tons of ionized gas, sulfur and oxygen, into space. This gas is captured by Jupiter's magnetic field and forms a giant torus, a donut of plasma encircling the planet in Io's orbit. The plasma torus rotates with Jupiter, completing a full rotation in 10 hours. But Io moves more slowly. It takes 42 hours to orbit the planet. Result: plasma constantly overtakes Io. It catches up with its own tail, created by the Moon one revolution earlier. And this collision gives rise to something incredible. Electrons accelerate along magnetic field lines. They fly from Io to Jupiter's poles, gaining energy in the thousands of electron volts. And when they reach a certain height above the giant's atmosphere, something happens that physicists call cyclotron massa radiation. Electrons rotating around magnetic lines begin to coherently emit radio waves, not chaotically, but in a coordinated manner, like a laser, only in the radio range. The power of this radio laser exceeds anything that the Sun is capable of emitting at the same frequencies. And these radio waves travel into space in narrow cones, rotating along with the planet. Jupiter turns into a slow pulsar, a cosmic beacon that sweeps the solar system with its rays every 10 hours. When the beam passes through Earth, our antennas detect a surge, then silence, then another surge. This model explained a lot, but not everything. The question remained: why do S-bursts drift down in frequency? Why does the signal start on a high note and then drop? Classical theory provided the answer. Because electrons move, they fly along the magnetic line from Jupiter to Io. As they move away from the planet, the magnetic field weakens, and the frequency of cyclotron radiation directly depends on the strength of the field. The weaker the field, the lower the frequency, hence the drift. This theory lasted for 50 years. It was considered proven, and then everything collapsed. The 21st century, a new generation of radio telescopes. The Ukrainian giant UTR-2 near Kharkiv is the world's largest decameter antenna. The French observatory in Nancy, American arrays, all of them are pointed at Jupiter, and all of them record data with a resolution that Burke and Franklin could not have dreamed of. Milliseconds, microseconds. Each S-wave can now be broken down into hundreds of individual points. And when scientists did this, they saw something strange. Zebra patterns appeared on the spectrograms, parallel stripes resembling barcodes. They did not fit into classical theory. Even stranger were the meandering bursts, S-shaped curves that first fell, then rose, then fell again. The same source seemed to be visible at several frequencies simultaneously. That was impossible, if you believe the old model. A group of researchers asked a simple question: what if we have been ignoring the obvious for 50 years? Radio waves do not propagate instantaneously. In a vacuum, they travel at the speed of light, but there is no vacuum near Jupiter. There is plasma, the very same torus of ionized gas, and plasma slows down radio waves. Moreover, it slows them down differently depending on the frequency. This is called dispersion. The same effect causes a prism to break white light into a rainbow. Low-frequency waves are delayed more, while high-frequency waves pass through faster. The signal, which was initially short and clear, becomes smeared over time. The classical theory of S-burst completely ignored dispersion. It was believed that the effect was too small to have any influence. But when researchers recalculated the data taking into account the variance, the picture was reversed. Frequency drift, that very falling signal, turned out to be largely an artifact. Not movement of the source, but distortion during propagation. When you remove dispersion delay, the trajectories of S-bursts change radically. And now for the main blow, the direction of electron movement. For 50 years it was believed that electrons fly from Jupiter to Io, away from the planet towards the Moon. Adiabatic motion along expanding lines of force. New calculations have shown the opposite. Electrons move towards the planet. Not away from Jupiter, towards Jupiter. They fall into the giant's magnetic well, accelerating along the way. This is not just an amendment, it is a paradigm shift. The mechanism that controls S-bursts turned out to be closer to what happens on Earth, in our own auroral zone, where kilometre-long polar lights are born. There too, electrons fall down towards the planet, generating radio waves along the way. Jupiter, it turns out, does the same thing, only on a scale that exceeds Earth's by thousands of times. And what about the energy of electrons? The Juno mission, which entered Jupiter's orbit in 2016, brought another surprise. The onboard Waves instrument detected radio bursts near their source, where no spacecraft had ever been before. Calculations have shown that the energy of electrons generating S-bursts is 23 times higher than older models suggested. Not kilo-electron volts, tens of kilo-electron volts. Particles are accelerated to speeds that constitute a significant fraction of the speed of light. Where does this energy come from? The answer seems to lie in Alphen waves, special plasma oscillations that propagate along magnetic lines. These waves are generated by the interaction of Io with the magnetosphere and travel to Jupiter, carrying enormous power with them. Somewhere along the way they break down, transitioning into a turbulent mode, and transfer their energy to electrons. The mechanism is still not fully understood. We see the input data, Io's volcanoes, plasma torus, magnetic field. We see the output signal, S-bursts flying towards Earth, but the black box between them remains a mystery. 70 years on, and we're only beginning to understand how this voice works. What has changed over the past 70 years? Let's start with the obvious. We are no longer alone on the airwaves of the solar system. After the discovery of Burke and Franklin, astronomers rushed to check other planets and found voices everywhere. Saturn turned out to be a radio source, quieter than Jupiter, but with its own character. Its radiation is associated with polar auroras and the rotation of the magnetosphere. Uranus and Neptune also speak, although we only heard their voices when the Voyagers flew by in the 1980s. Even Earth, our own planet, turned out to be a source of so-called auroral kilometre radiation. We shout into space without even knowing it, but Jupiter remains king. Its signal is so powerful that it sometimes drowns out the sun. At certain moments, at certain frequencies, the gas giant becomes the brightest radio object in the sky, brighter than the star that gave birth to our entire system. This made scientists think about things far beyond the solar system. If Jupiter screams so loudly, can planets orbiting other stars scream too? Exoplanets, gas giants orbiting distant suns, are theoretically capable of generating the same radiation, perhaps even more powerful if they're closer to their stars or have stronger magnetic fields. This opens up a whole new method of searching. We're used to searching for exoplanets by their shadows, when they pass in front of a star and slightly eclipse it, or by the gravitational wobble of a star under the influence of a planet. But what if we could hear them directly? Catch a radio cry from the depths of the galaxy? The project is already underway. The LOFAR radio telescope in Europe, a gigantic network of thousands of antennas scattered across several countries, is purposefully searching for decameter radiation from exoplanets, so far without success. But the technology is improving and sensitivity is increasing. Perhaps we will hear the first radio voice from outside our solar system within our lifetime. And what about Jupiter itself? The Juno mission changed everything we knew about the giant. It showed that its poles are covered with cyclones the size of Earth, which for some reason do not merge with each other, but spin in a strange dance, like balls on a billiard table. It discovered that Jupiter's magnetic field is lumpy, uneven, with dips and peaks that do not fit into simple models. It measured the depth of the famous bands and zones of the atmosphere. Some go thousands of kilometers deep, and she continues to listen. The Waves instrument on board Juno is essentially a radio receiver. It detects those same S-bursts, but not from a distance of 800 million kilometers, like Earth-based antennas, but from much closer, sometimes only a few thousand kilometers from the source. It's like the difference between listening to a concert through a wall and standing on stage next to the speakers. Juno's data confirmed that the S-burst mechanism does not only work in conjunction with Io. In 2023, a group of French researchers discovered similar signals associated with Ganymede, Jupiter's largest moon, and the only moon in the solar system with its own magnetic field. What's more, S-bursts generated by Jupiter's main aurora occur without any involvement of satellites. This means that the mechanism is universal. It does not require Io's volcanoes as its sole fuel source. All it takes is a magnetic field, plasma, and the right conditions, and the planet begins to scream. But the strangest discovery is not related to what we found, but to what we still do not understand. Remember the reversal in the direction of electron movement? We now know that they fall towards Jupiter, not away from it. But this raises a new question. Where do they accelerate? The old model was simple. Electrons are accelerated in the plasma torus of Io, fly along magnetic lines, and emit radiation along the way. The new model requires a different energy source. Alpha waves are the main candidate, but the details are unclear. Where exactly does the energy transfer take place? At what altitude? What mechanism causes the wave to break and transfer its power to the particles? We see the symptoms, but we don't understand the disease. Or more precisely, we don't understand health. Because for Jupiter, this is not a disease, but a normal state. He has been doing this for billions of years. And here another question arises, one that is rarely asked aloud. Could there be something else in these signals? In 2024, a group of researchers from the SETI project proposed an unusual method for searching for extraterrestrial intelligence. Their idea was that an advanced civilization might not use powerful radio beacons that reveal its location. Instead, it could hide its messages in natural noise, in signals that look like natural phenomena. Jupiter's S-bursts are the perfect camouflage. They are complex, chaotic, and difficult to analyze. If someone wants to hide a message in cosmic noise, there is no better place to do so. This is, of course, speculation. There is not the slightest evidence that there is anything in Jupiter's signals other than plasma physics. But the very possibility, the very fact that we cannot rule it out, speaks to how little we understand what we hear. 70 years ago, two scientists in a field near Washington mistook a signal for interference. Today, we know that it was the voice of the largest planet in the solar system. But do we know what it is saying? Let's take a step back. Let's look at the whole picture. Jupiter formed 4.5 billion years ago from the same cloud of gas and dust that gave birth to the Sun. It was the first, a gravitational colossus that gathered most of the material left over after the star's birth. If it had been 80 times more massive, thermonuclear reactions would have ignited in its core, and our solar system would have had 2 suns. But that didn't happen. Jupiter remained a planet, a cold, dark giant, warmed only by its own gravitational compression and the distant light of the Sun. And all this time, 4.5 billion years, it has been screaming. We have been listening to him for 70 years. That is 1/60 millionth of his life, a moment, less than a human heartbeat on the scale of the planet's existence. In that moment, we managed to be born as a technological civilization, invent radio, build antennas, launch probes, create computers capable of analyzing terabytes of data, and still not understand what they're telling us. This is not a reproach. It is a statement of scale. Space is not silent. It has never been silent. Stars emit light, pulsars pulse, black holes roar at frequencies we're only learning to hear. Planets, even cold gas balls on the outskirts of their systems, add their voices to this chorus. We were simply deaf for millions of years of evolution, until we had ears capable of hearing radio waves. And then, when we finally built them, it turned out that understanding words was a completely different task. Jupiter is not the only one who speaks. It is not even the loudest in the universe, but it is the closest. It is our neighbour. And if we cannot understand our neighbour, what chance do we have of understanding a cry from the other end of the galaxy? Perhaps that is the lesson. We tend to think of space as emptiness, a black abyss dotted with rare stars, silent, indifferent, dead. But this is an illusion. Space is an ocean of signals that we are only beginning to discern. Gravitational waves from merging black holes, neutrino streams from exploding supernovae, radio cries from magnetized planets. The universe speaks, constantly, in many languages at once. We built the first hearing aid in the 1930s when Carl Jansky accidentally discovered radio emissions from the Milky Way. We heard the first voice of the planet in 1955, thanks to Burke and Franklin. We sent Juno in 2011 to get closer to the source, and every time we think we understand what it's all about, it turns out that we haven't even figured out the alphabet. This is not a failure, it is a beginning. Somewhere right now, at this very moment, Jupiter is emitting another series of S-bursts. Electrons fall towards its poles, swirl around magnetic lines, and emit radio waves. The signal travels through the plasma torus, distorts, and breaks up into zebra patterns. It enters open space. 40 minutes later it reaches Earth. Perhaps someone is listening to it now. A student with a homemade antenna, an operator at the Nancy Observatory, an algorithm processing data from Juno. They will hear crackling, clicking, a distant noise like the surf, and they won't understand a word. Until then, they won't understand. But we listen, we take notes, we learn, and one day, perhaps in a year, perhaps in 100 years, someone will look at the spectrogram and say, there it is. That's what he was trying to say. In the meantime, Jupiter speaks. We listen, and that is more than humanity has ever had throughout its entire history. The silence ended, the conversation began, we just haven't learnt the language yet.